Jade Abbott. I work at Retro Rabbit. I'm also helping build the Kaleido NLP engine, which you heard about earlier. And my talk is quite general. I think a lot of people's are. This is our first Botcon, of course. And my talk is how to even process natural language. So far today, oh, that's going to irritate people. So far today, we've had the why, or the why not in much cases. Raymond presented a little bit of the how, but we actually need to do the do. So this is like quite an interactive session. Please, if you have a question, put your hand up. We'll run to you like halfway through. Feel free to interrupt me, because the more we've got talking back and forth, the more fun this will be. And I think the more interesting and more useful it will be for you guys. Cool. So first of all, I'll do a little bit of background on NLP and deep learning, what's happened in the past 5 years or so. The tools that we currently have available, a few of them. Then I'm going to present 3 toy problems to demonstrate just how easy it is to use these tools, and I'll mention their relevance to chatbots, since that's why we're here. And lastly, I'll talk about the hard bits. Considering it's so easy to use these tools, why is this such a big field, and why is it so difficult? So something we actually haven't talked about, maybe it's something that's obvious to everyone, but what is NLP? NLP is the ability of a computer program to understand speech as it is spoken. In real world, that consists of a lot of tasks that we need to do. From sentiment analysis, which is deciding whether something's is positive or negative, to question answering, which is largely what happens with chatbots, all the way to named entity recognition, which is picking out university names or names of people from like flat tests. And this description even can include machine translation, where you give it something in English, and then Google Translate is an example, gives you back something in whatever language you choose. Little bit of background on deep learning. In the 1980s, we had neural networks. They proved to be powerful, but not as powerful as we thought. Back then, we tried like a deep setup. We had multiple layers. Your traditional neural network, for those who don't know, usually has only 1 or 2 layers. But back then we tried multiple layers, and they weren't proving to be too successful. In around 2007, this is moving. Around 2007, we tried again with these deeper neural networks, and it turns out that with exponentially more data and really affordable GPUs on Amazon, which you can rent for a few dollars, things are going to be different this time. Something that's overwhelming as someone who's probably coming into this field right now is the vastness of it and the general like fast-pacedness of it. We've seen a few presentations today where they present something that occurred maybe 2 weeks ago. They introduced a new concept, or in the past month, or in the past year, things that were published academically are now being run on production systems. You started integrating it immediately, which shows you how fast-paced it is. It's very hard to keep up. There's new things happening every week. But on the other hand, there's a lot of help. It's a very open community. There are lots of tutorials, endless examples, and they're one of the nicer internet communities I've come across. They're always willing to help. You often end up speaking, if you've got questions on an algorithm, you'll end up in touch with the guy who wrote it, and he'll be helping out, maybe giving ideas, which is really great. In terms of our off-the-shelf solutions, we've got IBM's Alchemy. We've got Google Cloud Platform, which is quite recently, they've just launched an NLP engine. Microsoft Cognitive Services, I couldn't figure out the UI, so if anyone has, let me know. TextRaiser, which is using literally 1980s technology, like the old style of AI. That's it, it's comparable in performance to IBM, which is using deep learning. And Natural Language Toolkit was actually just an API. And then for chat specifically, we've got, as we've mentioned, with AI, API.ai. And there are also about 1 billion more. The more you look, the more there are, varying degrees of usefulness. But instead of these off-the-shelf tools, which are great, you can integrate with them, but at some stage you're probably going to have to, you'll be charged with them, or for using them. And let's say you want to actually build something in-house for whatever reason that has been described today. You've got hundreds of tools. So Natural Language Toolkit, NLTK, that's usually for your pre-processing, getting hold of corpuses, which is your data sets. Scikit-learn, that's got more, it's all the tools you need to go through a machine learning kind of academic process. From statistics to a lot of the older techniques, and as they go on, they start integrating new things, which is cool. GenSim, which is Word2Vec, which is what Raymond was talking about. Very similar to Glove and a whole bunch. Then you've got Caffe, CNTK, Torch, Theano, TensorFlow, Spark, MLlib, and these are all deep learning tools, and they've all got their advantages and disadvantages. If you want to figure out what you should use today for what problem, you can definitely go look. There's some really great resources. I think there's one on GitHub. I was going to post it and actually look at it, but I forgot to. right now, the big buzzword everyone wants to jump onto is TensorFlow, which I'd recommend now. They've sped it up. It can use multiple GPUs. It's really, really great. And then the older one is Theano, which has been around for a bit longer. It's good. There's a lot of examples written for it and things like that. So those are my personal favorites. They're also written in Python, which makes it easy to use, as opposed to some of them which are in Lua or Java. Now to my 3 toy problems. First of all, I'm going to show parts of speech tagging with NLTK. Now that's simple. That's just, naming a the as an article, for instance. Second, I'm going to do a music recommender based on a Wikipedia-trained work to vet, but specifically just the Wikipedia rock corpus. So it's just like we've downloaded all the articles related to rock, and we've trained a music recommender. And lastly, I'm going to do a text generator, as was mentioned this morning by France, which actually generates by character using what they call a long short-term memory neural network, which is a type of recurrent neural network, if you know anything about that. And we're going to be doing that with Keras, which is a beautiful library that sits on top of either TensorFlow or Theano and makes things a hell of a lot easier. Cool. For those of you who, I don't think anyone, it's a hard thing about doing a technical workshop and getting people to be interactive, is to download a lot of this stuff takes like a fair amount of time and data. But when you have the time, we're using Python 2.7, we're using Jupyter Notebooks, so I can show you all the code and you can play around. NLTK, Gensum, Keras with either Theano or TensorFlow, depending on what you prefer. If you want to use a GPU for training, you're going to have to use NVIDIA's CUDA. I am not helping anyone with getting that running on Linux. Like driver installation, I can't. I've lost too many hours. And I've put the things on GitHub. If anyone wants to go check it out, it's Jade Abbott /Botcon 2016. I've got it over here. If you want to have a look. And it's got some things. So it's there for you to go download if you'd like and set up. Cool. Any questions so far? Put hands up, interactive. Come on. Did I go too fast? Oh, you didn't? Oh, Jade Abbott /Botcon 2016. I'll tweet it or something. Hashtag Botcon 2016. You guys can find it. It doesn't matter because you just got a hashtag and scroll, man. I don't know how many people are tweeting. Alien Elf is my Twitter handle, @AlienElf. I don't know. Go figure. Cool. So what I've got running here is something called Jupyter Notebooks, which is a really great tool. If you're into Python, you'll be quite familiar with it. It used to be called Python Notebooks, and it allows you to just kind of run these snippets of code, rerun them, play with them. It's quite cool. A lot of integrations and stuff. So let's go into our first one, which is Natural Language Toolkit. I'm going to scroll to the top. Cool. So all I'm going to do is, first of all, just create something and show you how quickly and how few lines of code you can do something that just tags parts of speech. So like I said, what we're going to do, take a corpus or take a set of strings, which is this little snippet about Mr. Blobby, if anyone knows Mr. Blobby, and is going to output types of parts of speech. So to do that, pretty simple. First of all, we initialize our tokenizer, which is basically going to split up our words. And then we initialize our tagger. Our tag is a unigram tagger. That means it's going to tag every word. And we're initializing it with some tagged sentence from the Brown corpus, which I'll speak a little bit about later. Then to tag, it's simply a matter of tokenizing your corpus so that it separates it into individual words and just putting it into the tagger. And out will pop some tagged words. So let's run it. It's kind of hard to see in here. Let's wait 5 seconds. I think it takes a little while to load the corpus. Here we go. Cool, so now we've got each of the words that were in the corpus, and they've got like a little tag. These tags are not very useful right now, the little summaries. I'm sure some of them are verbs, and some of them are nouns. Some of them are definite articles, definitely noun. So let's quickly display what those tags mean. Cool, so some of them have no matching tags. There are a lot of them labeled none. These ones I can say, okay, cool. We found an in, that would be a preposition or conjunction. JJ would be an adjective or numeral, etc., etc. So quite easily, we've already learned a fair bit about our data. We can identify nouns, and that's just using very old school methods. Like I said, NLTK is something you'd use for pre-processing. It's something you do to, given a corpus, you want to tag things, you want to separate things out, you want to label stuff or group it together in certain ways. That's what you generally use Natural Language Processing Toolkit. If you want to do tokenize with a different one, we can use something called We can use an English, if you wanted to, for instance, separate them out into separate sentences. That's, okay, cool. Maybe you need something that can only take an input of an individual sentence, but these seemingly simple tasks, you always start to be like, nah, that'll be easy. I'll just be able to code that in 5 seconds. There are always nuances to these problems. That's why it's great to have libraries like this. So separating out into sentences, you just be like, just whenever it's an exclamation mark or a full stop, I'll just split it out. I'll have sentences. No, get something to do it for you because full stops are not necessarily always used to end the sentence. They're sometimes used in abbreviations and things. So quick little run. There we go. And we have each of these separated out into little sentences, which is cool. And you can see there's Mrs. Blobby somewhere here, had a dot, and it there's Mr. Blobby, it's fine. And it picked it up as like one single sentence, which is great. Okay, cool. So we spoke about corpuses. Once again, corpuses are usually used as either the thing you want to do natural language on or something similar to what you'd be, the natural language you'd be processing. This could be a Wikipedia corpus, it could be a number of things. I'll show you the options. So if you're using NLTK, you just go nltk.download, and then a little program pops up sometime today. There we go. Move that into view. Cool. And here's a list of corpuses that are available for you to download at any point. So a very popular one is the Brown corpus. It's quite an old corpus, containing a fair number of books, if I'm not mistaken. They've got a chat one. It's quite small, and quite old, but it's there if you want to program some chat stuff, which is quite cool. It's got a bunch of labels and stuff, which is great. They've got Project Gutenberg, which has a whole bunch of projects and books that mostly like well-known books that are now out of copyright. Oh, what's the word? Public domain. There we go. So that's everything from Alice in Wonderland, Shakespeare, etc. So you can use those to train your things, and you can see there are hundreds of them, all varying sizes, varying uses, depending on what you want to do. So it's great. You have these. You just download. You've got it. Some of them are large, 2.1 gigabytes. It's still pretty cool. So here I'm going to use, just pull in Jane Austen's Emma. Blah, blah, blah. Cool. And we've got all the words. I just basically got all the words from the thing, and now I've outputted like a snippet and the number of words. So you can see it's got that many words. Cool. So this is your first step. First step, most boring step, sometimes very interesting, is pre-processing your data. It has to be done. If your data goes in wrong, it'll come out wrong. Feed it garbage in, garbage out, I think the word is. Cool, so that's that part. Pre-processing, NLTK, very useful, used basically by every single other tool. Cool. Next one on to more exciting stuff. We're going to make a music recommender by training Word2Vec, which will basically take words, and in particular band names, on the Wikipedia rock music corpus. So that one, some guy went and just scraped those particular things. And so what we need is first of all, the band The Rolling Stones, that is one thing. We're not in the point where we can actually going to train it to learn that is one thing. So we'll give it a list of bands and be like, these are multi-word tokens, essentially. So all band names would be like that. We need the data set that's been scraped off Wikipedia. The entire rock genre has been scraped. You could obviously use more. And often use a set of stop words. These stop words, usually words are things that occur often, and sometimes they throw off a number of the algorithms. So and they're not really adding much to your knowledge about music and recommendations. They do have their uses depending on what type of list. So we've got a list of these guys. I can quickly show you them here. So that's all artists. It's a list of all the artists we've got. There's the list of stop words. Actually, here is the multi-word dictionary. So then it's like, okay, cool, this is a band name. That is one token. Cool. So, yeah. Yeah. So that would depend on how you actually did your filtering. So you can split up your tokens, and then what it should do is, and I'll show you what we do now. But in this one, it basically will look at an entire token and determine if that token is entirely a stop word. And then it would remove it. So if you've got Jerry and the Bandits or something, and the and was removed, it wouldn't be removed because it would look at the entire token and then it wouldn't remove it. I mean, obviously you can make that error, and things like that do occur in people not thinking, they're going like, oh, I've got data, stuff, there we go, results, and some things don't work out and they wonder why, and it's often because of little mistakes like that. So, oh wait, so I was going to show you that. Cool. So I was lucky enough that a nice guy on the internet, I've put the sources actually in the presentation, they're also on the GitHub, actually went and did this. So I was like, oh, cool example, I'll show you guys. And he went through the effort of showing how to actually train something with GenSim. So to us, from my perspective, it's a single method we call called train and save, and we just pass it these three things. This last one is just the folder containing each of the Wikipedia rock corpuses. I can show you that too, if I can get it on the screen. There we go. So that looks like this. Whoever that guy is. So that's just a single one. Yeah, this is a really huge folder. It's got like loads and loads and loads of stuff in it. Okay. So the training looks like, where are we? There. So most of this is pre-processing. So they've constructed a few different things. I think they should have used NLTK, but this guy chose not to. He's got the first one basically takes the entire very large dictionary of words and splits like single corpus and splits that into individual tokens, so our words. It does it in the specific way that it uses the multi-wordness so that we end up with single tokens representing bad names. Obviously that is something we could learn, yeah?
If you created a list of multi-word tokens with bad names, but if it's just going through the entire corpus, it will find the single words of the bad name. Wouldn't those interpret as well? How do you filter out those?
No, we split them out as that's part of the tokener. The tokenizer will basically see that entire large thing as a tokenizer. We don't have to do that. There are tools that will actually do the splitting up for us. This guy actually coded one, but there are in NLTK to do that. And then he builds a stop word filter, which you may as well just use the NLTK one. But the magic is all in this one line, if you can see it. That. Particularly the GenSim, as I mentioned earlier, is the library used for Word2Vec. And all we do is we say gensim.models.word2vec, and we feed it like, cool, this is where you need to go look for the files. Here's the tokenizers. And all we actually do is give it this like pre-processed batch of tokens. And we say, cool, this is our corpus, train. And that takes a little while, so I was going to run it, but then it takes about an hour to 20, like probably 2 hours to actually train. So you do that once. So I saved one. After I did it, saved it as this file. You can see it ends up building like quite a large model. Although I think that's only 18.8 megabytes. So considering that we've got that much data and it only makes something like that large is quite impressive. I don't know. I was going to do that, but it's very big. It's probably bigger. It took a while to download, so that just depends on our internet. Okay, so load up the corpus. I'll do that. When I'm clicking, I'm actually running these things, just so you know. Done loading, sweet. So we've got it loaded. So yeah, let's actually quickly have, before I do that, let's have a quick look at this word vector. So I'm going to look at David Bowie in honor. And let's have a quick look. I'm actually going to display this word vector so you can see what it looks like on a little graph. I'm using something called Matplotlib, which is really awesome, integrates directly into Jupyter Notebook. Cool, generates a little graph, and that means nothing to us, but it does mean something to the neural net. It does show the closeness of how these things are. And if you start rendering different graphs to different things, perhaps you'll start to see the pattern. I certainly don't yet, but there we go. You can see the size of this word embedding is 100, so that's 100 dimensions. If you're dealing with like the Google News corpuses, generally it's usually what it is. And GenSim's got some built-in things. One of the cool things is it's got something called most similar, which seems to be cosine similarity. They also have a cosine similarity, so I'm not sure the correlation. But if we ran that, we get the top 10 bands related to Joy Division. So if you know anything about Joy Division, they became New Order when Ian Curtis died away. So number 2 closest pattern in our semantic space is New Order. Sushi and the Banshees happens to be one of the starters of Goth, the same way that Joy Division was, and it's the next one. And you can see our recommendations, just based on feeding it like corpus of Wikipedia, just like that, it has learned which ones are nearest. Lady Gaga, if you prefer pop, is close to Katy Perry, Beyonce, Alicia Keys. And Queen is close to Freddie Mercury, obviously, and then it's got a bunch of Queen songs, which is really interesting, and Nelson Mandela, and Sting, which is interesting, Leonard Cohen, and then, yeah, We Will Rock You. But because this corpus didn't only consist of, our dictionary didn't only consist of these bands, we also have some other things. So it knows about drugs, and it knows that alcohol is closer to drugs than heroin, apparently. And it's got alcoholism down there. Prescription, that was, I suppose, pretty good. I was quite proud. Substance, you know, so it's learned these things. We haven't told it anything explicit about this. It's just learned this, which is really great. This is a cool one, this last one here. This is New York and London, and it knows that New York is the same as NY, is near Los Angeles, is near, like, got Manhattan, the Bay, and then if I gave it London, which is the second one down here, Manchester, Liverpool, Glasgow, England. So it's even learned about the location of things, which is absurd, actually, given that we just shoved it a bunch of data and it spat this out. Once again, I trained this on my laptop using my tiny little GPU on here, and it took 2 hours, and it's already learned a lot, and I never had to give it a second thought on how to do it, which is really cool. So would anyone like to propose something that we check a word for? Someone give me a band name. Yeah. I don't even know. Billy Talent, that's probably a good one. We can do that one. And you'll see the more popular the band, the more it knows, the more accurate the predictions are. If it's a very obscure band, which we can always try. Every Time I Die. I guess that's close. That's going to put Arco. Bring Me. Interesting. Parkway Drive. That works. Bring Me. I don't know. It's kind of in the same... It is, okay, fine. Same era? Yeah. I don't know. They were kind of the same-ish era, I guess. Kill Switch. I guess, to be fair, everything on here seems closer to each other, but... Yeah, I think it's pretty decent. Anyone else? A random word, for instance? A place and anything? You go. Amend it. Depends on, I don't know if you can do that with Word2Vec. There's a lot of models you can just feed it more data and continue training. Some of the parameters aren't perfect because, you know, the longer something trains, it often does hyperparameter optimization and things like that. But a lot of the time, I know Keras, for instance, you can take a model and you can just continue training that model because essentially it takes randomized weights anyway, and then it can just make those a little bit better over time. But I think GenSim, at least, it's probably in there. GenSim, from what I see, is you just retrain it again, but it doesn't take long enough to worry about it. Like, thinking up rules ahead of time would take a lot longer than the amount of time it takes to train these things, you know. Any other questions so far about anything we've done? No. So all we're doing is we're actually saying most similar. We give it a positive thing, so that'll be like it's got an empty vector and it's adding on this vector. If you added this, you can also specify something negative. So give me things that are related to this, but remove that bit, unrelated to that. And then we're specifying we just want the top n, so we just want the top 10. Can change that to 1 or whatever. If I chose Every Time I Die, it's just going to go search, move where it's searching. So it's searching in the semantic landscape. Let's assume it's just like a physical landscape. And right now it's centered around, what did we do? Billy Talent. So if we move it to Every Time I Die, which is maybe up here on the mountain, just over there, then it'll just find the 10 most similar bands around around that one, yeah.
So these vectors are basically positions.
Yeah. Yeah.
The fact that Every Time I Die was close to Billy Talent, isn't that sort of...
Yeah, so it should be the other way around, yeah. So we can...
Basically, if you add Every Time I Die instead of Billy Talent, it should be the same list. Except
Yeah.
those two should be swapped. Or you
Let-
should at least get Billy Talent.
Let's do this, and we can play. No. And I can tell you why that will be. Or why it could potentially be. You've got so many dimensions, right? So Billy Talent might be far away from a lot of things, whereas a lot of things are near Every Time I Die or closer to Every Time I Die. So it might even be on the one side that it's closer. So it does have the potential to do that, of course. Yeah, so that would be my answer. Any other questions so far?
20 27, that age 27.
27 club.
Yeah, the 27. I want to see what it returns.
Oh, I wonder if it has it as a token. So I think it might have stripped out, I need to have a look, it might have stripped out digits. Because I think I tried 65 days of static and I didn't have it because it removed anything that had numbers because it didn't learn numbers. But we can try 27 club. It'd probably be like, this does not exist. Yeah, there you go. 27 club is not in vocabulary. 27. You guys really want to see this? Is that how Wikipedia would have it? No, it doesn't like that one. Because it's probably not a single token. So it probably we didn't give it like, okay, cool, this is a dictionary that we actually need to run off. So it's probably got 27 club. You can give it Nirvana and see what happens. Kurt Cobain. Who is that? That's interesting. And at least got, yeah, I don't know why James Hetfield's closer, but anyway. Yeah, so then it's got Nirvana and it's got Courtney Love, so it's picked up a few things. I don't know why. I think Owen Curtis and Jim Morrison were all in the 27 club, actually. That I think they were, and Dimebag Darrell I think was as well. So, yeah? Where's he? The drummer, the drummer from Nirvana. Wasn't that Foo Fighters guy? Anyway. Oh, okay. Okay, there we go. Okay, that makes more sense. All right, cool. So this is pretty interesting. In general, when you're doing this, unless you're working in a very specific corpus, you don't usually have to retrain it because they've got a lot of publicly available ones. So you can go to, I think the Google News one is very, very much used. That's the one we use for most things. It's very general. It knows about a lot of things. And it's just a matter of downloading the corpus, saying, hey, Jensum, use this, loads it up, and then you're ready to go. And now you've got this way of relating data. And this is just the most simplest application. There are hundreds of things you can do with these word vectors, which is quite cool. Yes, Reynard?
For example, the Google News, it was mentioned earlier today that kind of it may be a bit biased to American news and big forwarded into celebrity.
Yes. Yeah.
So can it be an issue, if you have a specific application you want to focus on? You can't, do you actually kind of have to retrain it or use it as is, or can you try and amend that, or is that, is it easier to, just retrain your own thing, or can you actually work off the base they have, but teach it more about?
And I think that's exactly what I think Hugo asked. Similar. So I don't know if Jensum you can, but in general with these types of things you often can. I don't think people traditionally do because it's doesn't take not that hard to retrain again. But I know, like I said with Keras, if you're using like other types of neural networks, you give it the model, it can only improve on those weights. That's how you initialize it, right? So then you can just improve them a bit more over time. Yeah. And also, but the other things, if you extend the range, so cool, if it's got, let's say, it's trained on these words, if you want to add words on, that's a different story. So they've got different ways of doing that. Sometimes they try embed those new words into, I've seen that done before in a paper that was published last year. They try to take these new words and figure out how they relate to other words in the corpus and like embed it that way, which is really interesting. But yeah, if you're adding words, then I think you usually you'll get the best results if you train it from scratch. So that's it. I haven't played, so you're welcome to go home and play. So yeah, okay. Anything else before I move on to the next one? We cool. Cool. So we're going to train a long-term short memory to mimic the writings of Nietzsche, because that was a corpus I found. To give you a little bit of overview on a long-term short memory, a long short-term memory, I always say that wrong. So what this is, I think Franz was talking about it earlier. We're talking about RNNs earlier. It's a type of recurrent neural network on RNN, which is a type of deep neural network. And what's specific and useful about, and particularly for natural language, is recurrent neural networks act on sequences. So if you give it a sequence of input, it will look at each item and try to remember the importance of the previous items in order to carry that through to the next ones. So it's very useful in natural language. In anything else, it's music it's good for because that's also sequential. For speech recognition, it's also very good. But for images using convolutional neural networks. Cool. I've got some links at the bottom there if you want to find out some more information. Obviously, you can't see this. I'll tweet this and I'll put it on the link as well. I'm sure we can get it up on the page too. And then you can go have a deeper look at how these things work. But as like a brief overview, A normal neural network would just, it's a feed-forward neural network. They take some input, they feed it through, and then they get an output, and then they backpropagate that change, and that's it. What happens with a recurrent is you feed it a token at a time, and each token, they save some part of the state of that weight. So they save some internal state. And so as they push it through, they're remembering bits of this state. And when they backpropagate, they call something called backpropagation through time. So what this is over here is like an unraveled recurrent neural network, where this is time 0, you've got time 1, time 2, all the way to time t. And basically, this shows you that as time 1 goes in, time 0, we use the state of time 0 to influence what we understand at time 2. And that 2 is also used to influence what's understood at time 2 and 3 and all the way to t. And these little h's are like the hidden state that we say from it, which is cool. Okay, well, there's a picture. You probably can't see any of it, and I wasn't going to describe it in detail anyway, but that just shows you the internals of a long short-term memory, which is to try, is better than a normal RNN because it tries to capture, remember these things for a little bit longer. So it tries to not, by the time you get to the end of the sentence, it tries to not forget everything that happened at the beginning of the sentence, because that's what tends to happen with backpropagation. Cool, so the way we're going to train our long short-term memory is we're going to take a sliding window of 40 characters, and we're going to use those. This is how we're going to construct our training set. So we've got our big corpus. We split it up into chunks of 40, and our target character, so the thing that you're trying to predict, will be the target. So that'll be the next character that does occur after 40. So I'll show you what the code looks like now. Then we shift our window by 3 characters, take those 40, feed them in, those 40, and then our target needs to be the character after that. We do that for the entire data set. So we end up building a very big data set from our corpus. And the idea is that, so you've got this data. You take each of those characters, and you convert them into a one-hot vector or embedding, as Raymond displayed earlier. And that basically says for every single character, it'll just have like a load of zeros, and then it'll pick like, A will be number 0 and B will be 2, for instance. So when something is an A, it'll just have a 1 at the beginning, and everything else will be 0. So it's just very inefficient encoding, actually. So your input will be 40 of these, 48 or so length vectors, one-hot vectors, and your output layer is simply that the number of characters. So it will have nodes. It'll have a number of characters. It'll have nodes equal to the number of characters in the set, or the number of unique characters. And what it usually does is we're using a softmax. So if you've ever done anything about probability, it'll predict the probability of that of a particular character occurring in being the next one. So if I give it 40 characters, it'll output like, okay, the most probable next character. So let's say that is D. D will have a probability of 0.8, for instance, and everyone else's would be very, very low. So that's quite hard to follow. So if you didn't gather that, that's fine. You can go read up on it. It's quite intense. It's really hard to try explain it as well when I don't have like things to draw. Okay. So, like I said, I'm using a AI library called Keras. Really cool. Makes using things like Theano and TensorFlow even easier. It sits on top of that. It's one of the guys from Google. I've forgotten his name, but he's a lifesaver. He's very cool. Recommended to run the script on the GPU because they're very, very computationally intensive. If you're going to try the script on your own data, try and make sure you've got at least 100K characters in your set, or closer to 1 million is better. In fact, the rule is with most deep learning, the more data, the better. When people ask how much data do you need, you just be like, more. And when you've got more, be like, well, how much do you need now? We just need more. The more you give it, the better it gets. So let's look at our little corpus. We have, it's going to, oh wait, I didn't run that one. Where are you? Yeah. Okay, that's better. Cool, so this just takes the corpus, reads in the entire text file, outputs the length, and the total number of unique characters. So it's got 58 unique characters. This is probably including punctuation and numbers and other things as well. We've also noticed we've taken the lower case because that gives it less things to train on. So the less thing, you're actually downsizing the search space, which is quite cool. So here we're creating these overlapping windows We've got a window and its target character, and we built up these two sets. They're calling these little windows, I call them sentences here. And that's essentially from these 40 characters. And then the next chars is going to be a list of what the predicted character for that particular sentence is meant to be. So you've got these two parallel lists. I can run that too. I think this one takes a while. Oh wait, not really. Cool. Number of sequences, so that's essentially the number of data patterns we've got, which is cool. Great, this little tiny bit of code generates a one hot vector. Super simple. All that does is basically take an array for the size of the number of characters and maps each of those characters to one thing in the array, and then you get this like vector which has, like I said, one where the little, where it's meant to be the actual character. Cool, then we coded those. You can double check the size of the patterns. There are 40, which is correct, because we know we've got a window of 40. Cool, and this is the beauty of it. This is Keras. This is setting up the neural network to train in 5 lines. So that's compiling the model. So usually when you do this, you've got loads and loads. If you're manually building this yourself, it's hundreds of files trying to figure it out, probably with errors all over the place. And now you've got to pick and choose which type of thing you're going to use. And here, it doesn't matter. All the important part is what you're using, which neural network you're going to use. You can do a lot of hyperparameter optimization a lot easier. You can play with multiple layers. It's so easy to add another layer. So describe it to you. This just initializes what they call the sequential model. Means we're going to define it sequentially. This long short-term memory, which is one other thing to code, is one line of all that hard RNN work. You specify length, which is 40, and the number of characters. We put in a dense layer on the output. So that was basically, we'll take all the outputs and map it to a single unit, which is a softmax. And softmax is going to output this range of probabilities, and the one with the highest probability is most likely to be the next word. And then we compile it with categorical cross-entropy. Categorical cross-entropy are used mostly when you're dealing with softmax. And we're going to use an optimizer called Adam, which beats your usual stochastic gradient descent. It does a bunch of hyperparameter optimization and things. What we do want to do is inject, because we're creating something, we're essentially going to generate text. We're going to give it a little sample, and it's going to generate something in the style of Nietzsche. We want to give it a little bit of randomness, because I guess why not? It makes it more fun. It also makes things less valid. You can test it with different diversities to see how crazy it gets. At very low diversity, I find with long and short memory, it does a lot of repetition. So it'll get into almost these cycles where it's trying to do the same thing. In fact, Francis' presentation, he also had something where it kind of looped on the same kind of sentence over and over again. And this is dealing with these character encoders. So now the actual training. I just print out the diversity we're using, and our training is one line. That one. That's it. So you press that, and then you run that, and you let it to run for 2 hours all night, whatever. I'm setting it up to run through a batch size of 128 patterns at a time, so before it does its little backprop. Then we're going to do only 20 epochs, so that's 20 times it's going to run through the data. And that's very low. Usually you'd make that much higher, but I didn't have time, and the first time I did it, my laptop crashed, and I was just like, nah, I'll run it for 20, even if it's rubbish. This first input is the one we've got up here. Where are you? Which is basically going to be the input into this. So it's this set of one hot vectors, 40 of them, from the previous set that you were trying to predict. And then the second one, Y, is this list of target characters. So it's your targets, what you're trying to train your neural network to predict. At the end, you save the weights. You can basically save the weights of the model, can output it to JSON, save that. So that means you save the architecture, so that saving it to JSON, you save the architecture, so that's saving the number of units, etc. And then later on, we can also just load in the weights so that we have a pre-trained thing. So this is what training looked like. And you can see we started out around 2.5, and we went all the way down, not very far, to 1.5 in 20 epochs. Like I said, it's about 2 hours of training. And now we can load them back in. Load weights. Run that one because I think it was important. Okay, cool, it's done. Now we've got a little sentence. I want to show you what our model predicts in the raw form. Cool. So this thing here is the output of softmax. You can see those are mostly really like tiny little numbers. The things that are going to be most... So what this does is says, cool, for 400 iterations, take a sample sentence, which I've specified up here, which was those who will not inherit the kingdom of, or O. We're not even going to go O, because that's 40 characters. We give it that as our seed. And now we ask it to continuously predict the next character. So it'll predict the next character, then it will shift that window, so it'll take away the first character of the bunch, use that new generated character to feed to the next bit again, and it does that 400 times, so we actually get a fully constructed string. And you can run that. Did you run? You're not running. Why are you doing that? Hold on. Oh, there we go. Sorry. It usually has a little star when it's doing something, and it didn't have the little star. So let's read it. You'll see how awful and great it is, but it seems to have learned words, which we didn't teach it about words. We just gave it a list of characters. Some of those words aren't real. That might be because of our randomness. That might be because it just hasn't had enough time to learn them. So the first sentence is, to those will not inherit the kingdom of the sense, of the reeling, find of the power, of the distinction. In the still one has a delight to phology, and speak the browsing of who to say. So we can continue about that. And if you generate these a few times, you start realizing it's like, it does sound a little bit like Nietzsche. It starts talking about religion and existentialism and like philosophy, and you're like, okay, cool. We've got little Nietzsche here. He's a little bit small. He doesn't really know how like words work, but he's trying. So we've gone and done that, and I think that wasn't even like 100 lines of code, if that. And we've gone and trained something very basically to we didn't tell it anything, we just fed it text. And now it's learned a little bit about words and things like that, which is, like I said, is quite primitive. So any questions on how that one worked? Before I continue on my last ending spree. Yeah, so that was one of the things I was going to add. So because we've got this word-to-vec thing, wouldn't it be cool if we take text, use word2vec to convert that text into vectors? Then the same way we're feeding character by character in, because a one-hot vector for all the words is very, as we've described Raymond described in the previous one, it's semantically pretty useless. Whereas if we feed it an entire like word embedding, then it's already got that context. And we feed each of those in one at a time, and you'll start getting very interesting results. That's what I wanted to do next, but I kind of was stuck between like, but it's going to take a while to train and da-da-da-da-da. But that's pretty cool to actually do. So yeah, so you can. Next. You had one? Oh, really? Okay, cool. Where were we? Oh, I left that one out. Oh, well. Cool. The relevance of my examples, they're pretty random, but they're all kind of useful. So first one, NLTK is excellent for pre-processing and finding corpuses to train on, particularly when you're just a beginner or you're going to do some academic work. But it's also got some really useful ones from Wikipedia, which are very general. Word2vec or Glove, which are the word embedding tools, are used these days in just about any NLP application. They're very powerful and they're very important. And I said, though character generators are very simplified, the long short-term memory can be combined with word embeddings instead to give you very precise results, which is the question you ask. So my challenge to you is if you find this cool and you want to do this, and particularly that feeding in word embeddings rather than actual characters, I found this great link for chatbots yesterday. So I didn't have time to train it, but I think everyone should probably go give it a go. It's with Tensorflow, which is all new and shiny. It's using the corpus that's actually on NLTK. It's one of the corpuses available, so it's all stuff that you've kind of heard about today. And yeah, so it's pretty kind of cool. So my last slide seems easy. That was maybe 7 lines. That was actually neural network related. Everything else was pre-processing, and there was more lines, I think, displaying the data than actually training the neural network, which is upsetting. So why is this field still so hard? And I think if there's anything we've gathered today, it's like, yes, it is still hard, and we're still figuring out how to do it. Building bots is easy. Making things understand natural language is hard. Number 1, knowing your domain. We've had instances where people don't speak in proper English. They don't speak in normal sentences. So if you train this beautiful neural network on like Wikipedia English, and then you find out, turns out humans just kind of use shorthand and don't really finish their sentences, and everyone misspells everything, then you're going to end up with very bad results, and we've seen that quite a lot. Knowing your data is the hardest thing about it, because data is, you get all this stuff, and often you find it's skewed in some way, as you've mentioned, like it could be skewed to just like a male view. There can be something called data leakage, where you've got stuff in the data that's irrelevant, but it's still helping predict a result. So you're getting these very high training, like low training errors. So it looks like it's doing well, but it actually cannot generalize at all, because it's using this one factor that shouldn't even be in the data set. So knowing your data is hard. It's also hard to visualize. It's hard to visualize what you're missing or what you need to like give more of it. That's very difficult. And then knowing the algorithms. We've shown to use the algorithms is very, very easy. But to pick the right one with the right tuning, that is another field of study entirely. I suppose it is one of the main ones, is studying all the ones. And then the hyperparameter optimization on those is also very difficult. So what they say is a good approach, and it's stuff we've done, is try to visualize your data as much as possible. Often very difficult when you're dealing with this type of data, but if you just keep up to date, they're constantly publishing, they've realized this is a problem, and they've got a number of tools that help you like visualize this kind of stuff. Build a prototype on a sample of your data, because you'll learn a lot through that, always. And if relatively successful, optimize, analyze data, analyze further, and give more data. So yes, that summarizes, well, that's me. I sped through that. If I need me to go back, I'll explain something. Any questions? Benny. Yeah. I think they would be, because as soon as it's very small, yeah. I don't actually know. I can only imagine. Too large, I think larger should be better. Can you think? It's probably better, because often what happens, okay, so what happens technically, and this is probably where it would happen, is that the bigger this gets, you've got more, by the time it gets to end of sentence, it's got more chance of losing the information at the beginning of the sentence. So even if it was really important there, that can often get lost. But all these models like long short-term memory and GRU and all these new ones are basically built to try alleviate that problem, because what's happening is it's called the vanishing gradient problem. So by the time it's back propagated towards like the end, it's kind of like lost that information, or it overwrites it because they become too big or too small. So I'd say it is probably quite sensitive to some extent. I don't know. There's probably a range with you can work. I don't know. It's really easy to try. You can just change it, and then it's one parameter, man, and it's done. Anything else? Yes.
Just two quick questions. One is on the, as you've kind of gone through, and a lot of these different pieces of the model, it's different. It's often like two different open source technologies. There might be like Cloud and Word,
Yeah.
Piano versus Tensorflow. What are the criteria that you use to kind of sort?
Switch one.
And then the second question would just be on the forks. As you said, most data forks don't really fit here. So how do you find like the least bad forks? They're all going to be bad.
The least bad. Yes. So I'd say, okay, so on the first one, Word2Vec or Glove, I asked that same question. There were claims that Glove was better, but everyone in practice has said that it is the same. It's more or less the same. Some's are better. So I would say there's no choice. You pick one and you use it. They're pretty easy to switch with. Gensim's, I actually went through this process because I was like, maybe one's better. I don't believe people on the internet. One's better. And then I tried it out and I was like, yeah, they're kind of the same. So you can actually substitute in Glove with Gensim. You can make it use like a Glove format, which is cool. As for Theano and TensorFlow, that's a bit more of a harder question, and I've considered which one might be better. So it depends on your need. What I like about Theano, it's been around for a lot longer. If you have an idea for an algorithm or something, or you want an example, there's loads and loads and loads of stuff. Every researcher, most of them actually have worked in Theano, and they get a lot of stuff done in that. TensorFlow is not as long, it's only a year old, as we said, whereas Theano is quite a few years. That said, they put in a lot of effort into making it good to use. So I say in the past few months, they've just put out like a lot of stuff to say, okay, cool, we can use this now. They even said it can run on Windows. I don't really believe that, but CUDA runs better on Windows. But anyway, NVIDIA hates Linux. Stupid things. It's making them a lot of money now, so they probably should start paying attention. So yeah, so on that regard, like the choices on that one, you can look online. People say, okay, this one's better in production because it's faster. This one, is more algorithms, blah. There are lots of those. And then as for the data sets, I'd say the better one is the bigger one. So the one that has more is more likely, hopefully got a chance of capturing those things that are within your reach. But like, depends what you want to do. I mean, I think a really good exercise would be for South Africa to gather data from everywhere, from news articles in different languages, and just start training these things, which would be really interesting, because that's the only way I think you're really going to get a good one. Otherwise, I'd say bigger is better. I haven't found anything I'd like to say otherwise. So, yeah. I'd say, yeah, Wikipedia perhaps is a little bit, it's more scientific in some way. That said, they'll still report on whatever the internet was interested in. So the internet, Wikipedia may not have enough on Africa, It's not going to know about all our different people, whereas it'll have hundreds of pages on European history and American history. So still always go for more is better. Hope that answers. Anyone else? Stop looking so sad. It's fine. Okay, cool. Well, then I'm done. I just want to give a shout out to Belinda. I don't know if she's in here. I think she was presenting next door. But earlier, Gustav said, he thanked me and Belinda, and I just want to say it was majority Belinda. I got a couple of people here and some speakers. But most of what's happening here is due to the venue, Gustav, and Belinda. So thanks very much, guys. You did an awesome job, and I think we had a great day today. So yeah, so everyone go enjoy drinks and your weekend, I believe.